Okay, this is question 2 on the 2026 AP Physics C Mechanics free response section. And here we have a projectile of mass 4m being launched from the ground at an initial velocity v naught at time t equals 0 at an angle of theta naught theta above the horizontal. And then when the projectile is at its highest point in the trajectory, it's going to split apart into two different pieces, piece q of mass m and piece r of mass 3m. And it looks like piece q, based on the figure, is going back towards the left, and piece r is going towards the right at that highest point. So we have two times to consider. At time t equals t1, that's when the projectile breaks apart and the two pieces are moving away the opposite direction from each other. And then the second time is at time t equals t2, piece q reaches the ground and piece r reaches the ground. And it looks like piece q reaches the ground back to where it was originally fired from. So it should have the same horizontal speed going backwards at that point than it did going forwards to get to that same point. Okay. The horizontal and vertical components of a momentum vector are represented by px and py respectively. The shaded bars represent the components of the momentum immediately after t equals 0. Okay, so if we think about at time t equals 0, we had a mass of 4m going with speed v naught at an angle theta, which means we had a component going to the right, that is 4m v naught cosine theta, and then a component going up, that is 4m v naught sine theta. And so those are probably those two bars, the x and the y components. So we need to draw shaded bars to represent the x and py at time t equals t1. So at that highest point, there is actually no vertical momentum, since their vertical velocity should be 0 for both objects once they split apart. So I think these should both be 0. By drawing a distinct line on the 0 momentum line. Okay, so we will actually make sure we draw a line right here for py to show that those are both 0. And having 0 above it should probably help as well. Okay. If we think about the collision process here, or the explosion process, we're going to have before the collision, we have a mass of 4m moving to the right with speed v naught cosine theta, which is that initial bar in figure 2. Then after the collision, we'll have piece q with mass m moving to the left with speed v naught cosine theta. So it should have the exact same speed in the opposite direction in order for it to return back to its original point. So that should be essentially 1/4 the momentum, as that would be negative m v naught cosine theta, which is negative 1/4 the size as the original momentum that we have shaded. So we need to draw a bar that is 1 units in the negative direction for piece q, since the original one was 4 units tall. So we'll draw something like this. And that should do it. And then now we got to figure out piece r. So piece r has a mass of 3m, moving with some final speed vf. Let's actually calculate that final speed. We could do something like a conservation of momentum scenario. So we'll look at that, conservation of momentum. So our initial x momentum was 4m v naught cosine theta is equal to the momentum of piece q, which is negative m v naught cosine theta, plus the momentum of piece r, which is 3m times its final velocity. So we need to solve for that value. Divide out the m's, we'll get 5m, oops, m's are already divided out. 5 via cosine theta is equal to 3 vf. So that final speed should be 5/3 v naught cosine theta. So 5/3 as large. Perfect, which is really something like 1.67 v naught cosine theta. Either way, we're going to take that and calculate the momentum. So the momentum of piece r should be 3m times 5/3 v naught cosine theta. That cancels, and we should get positive 5m v naught cosine theta, which is 5 times as large as the momentum of piece Q, but positive. So we'll go back and shade that in. So it should be something like this. And that actually shows that when we actually combine these two bars, we actually get the exact same amount as we have for at least the x direction. And that's because if you think about the force diagram on these objects as they are moving through the air, they're classic projectiles, which means we have a external gravitational force that's causing the vertical momentum to not be conserved. There is that sort of external force there, but horizontally, because gravity is only straight down, there is no external force. And so the horizontal components of the momentum should be conserved during this process. So I think that's everything for part A. All right, part B, derive an expression for x2 in terms of v naught, theta, and physical constants as appropriate. Okay, let's draw this out. So we have, it's part B. We have our 4m being launched, speed v naught at an angle of theta. This is going to launch in the air, split apart into m moving backwards with speed v naught cosine theta, and then piece 3m moving forwards with speed 5/3 v naught cosine theta. And then at that point, this piece is going to continue on down and hit here. And then this other piece, piece Q, is going to return back to where it started. And I believe x2 is the total distance to the right. Okay, so we're looking for really this distance right here. That is going to be x sub 2. Okay, perfect. So we need to find an expression for the time it takes to get from maybe here to here, and then this expression. And I believe T2 should be 2 times the length of T1. So if this is a perfectly symmetric scenario, the center of mass really of the system, it's going to take the full amount of time to reach its highest point vertically and then go back to its original spot on the ground. And so the total vertical displacement should be 0 for that. Actually, we can probably do that here to get an expression for T2. So we could say in the vertical motion, the total displacement is going to be 0. The time is going to be T2. And we know the acceleration is going to be downwards at a rate of 9.8 meters per second squared. And we could probably solve for an expression. And we know the starting velocity. That's key. So the starting velocity in the y direction is v naught sine of theta. So given all that, we should be able to derive an expression for the time t2 in terms of the other variables. So we'll use this equation, delta x is equal to 1/2 at squared plus v naught t. So in this case, we'll have a 0 displacement is equal to 1/2 times negative g squared plus v naught sine theta times t2. We'll add this over and we'll get g over 2 t2 squared equals v naught sine theta t2. Cancel out one of the t2s. And so the time it takes for the projectile to launch and then come all the way back to the ground is equal to 2v naught sine theta over g, which also tells us that t1 should be half that time, should be v naught sine theta over g. And that could actually be solved in sort of a separate scenario by saying, since that final vertical velocity is 0, that should equal the original velocity plus at. So 0 is equal to v naught sine theta minus gt1. So we'll get that expression. So it really is a symmetric scenario where t1 is half the time for t2. And if we think about sort of the horizontal velocity time graph for piece R in specific, we'll try and draw that out really quick here. Let's add a second page. So that graph should look something like this. Actually, it's always positive. And so at T1, it's going just at a constant V naught sine theta. But then after the explosion, it sort of jumps up to T2 at 5/3 V naught sine theta. And so we could just say the actual total displacement traveled is the integral of this sketched velocity time graph. So that should just be V naught sine theta times T1 plus 5/3 V naught sine theta times T2 minus T1. So sort of this section here. So we have the area of that rectangle, and we also have the area of this rectangle. And then to substitute our values for T1 and the interval T2 to T1, those are actually the exact same times. So it should just be V naught sine theta over G. That's T1. So that means that total distance traveled is V naught sine theta over G times V naught sine theta plus 5/3 V naught sine theta. I think that should be the answer. And of course, if you wanted to simplify this a little bit, V naught sine theta over G plus 5/3 V naught sine theta. Sorry, V naught sine theta plus 5/3 V naught sine theta gives you 8/3. So yeah, 8/3 V naught sine theta. So it should be 8 V naught squared sine squared of theta over 3G. I think that's the simplified expression. And that's x2. Okay. Let's move on to part C. The horizontal component of a velocity vector is represented by v sub x. Figure 4 shows the horizontal components of the center of mass of the projectile as a function of t all the way up to t1. And we are asked to sketch a line or curve to represent Vx as a function of time for each of the following. So Q, R, and the center of mass. Okay, perfect. So we do remember that that velocity was actually V naught cosine of theta. And then after the collision, the velocity of object Q, I believe, was negative V naught cosine theta. It had to go the same exact speed, but in the opposite direction. And we ended up getting the velocity for piece R being a little bit faster, 5/3 V naught cosine theta. So let's actually graph all that out. So negative V naught cosine theta would be down here. So that's piece Q. 5/3 V naught cosine theta would be up here. So that's piece R. And the center of mass component should actually be exactly the same. And we can see that here. This is the center of mass. And it is a little bit closer in value to R compared to Q, and that's because R is actually 3 times as massive as Q. So I think that should be it for part C. We've clearly labeled all lines or curves. Perfect. And the last part D. Consider a case in which the projectile is launched at the same angle and initial speed is initially described. When the projectile breaks into pieces Q and R, piece Q falls straight down, so it doesn't go back to its original launch point. And in this case, piece R reaches the ground at a new location, x nu. Indicate whether x nu is greater than, less than, or equal to x2. Okay, so it should actually be less than, and we'll actually try and justify using both A and C. Let's start with part A, actually. So let's talk about this. Okay, so for part D here, we could say that the new distance should be less than the original. That's going to always be true. So if we want to use our reasoning in part A, we had an original bar chart that showed that the x momentum was 4 units tall, and that should equal, for Q, a x momentum that's actually going to be 0. And this is because it falls straight down, which means after the explosion part, the final horizontal velocity is 0, and Q just falls vertically. And so if that's the case, in order to conserve conservation momentum here, due to conservation of momentum, that means that the horizontal component for R should be the exact same amount. So it should just be 4 bars instead of 5. So we'll have less horizontal momentum for part R, which means less velocity forward. It will take the same amount of time to fall, so it's going to still reach the highest point. So same amount of time in the air. Also same acceleration. It's still just the acceleration due to gravity. So less distance traveled horizontally. And that should do it for part A. And if you wanted to use part C, we had a velocity as a function of time graph. So we'll sketch that out. We have the center of mass velocity here. At time t equals 1, that's going to continue on. So that doesn't change. But now piece Q is going to be down here. So this is Q, which means R is actually going to be a little bit less. So because the center of mass V doesn't change, if Q is no longer moving backwards, really it's a velocity, then the velocity of R does not have to be as large forwards. And really the expression here is that the velocity of the center of mass is equal to the velocity of Q times the mass of Q plus the velocity of R times the mass of R over the total mass. And since this term is no longer negative, it used to be negative, now it's going to be 0, then that means as it goes from negative to 0, then V sub our value for the velocity for R is going to be a lot less. In fact, you can actually derive this out. We could say 4m times the velocity of the center of mass minus m times the velocity of Q is equal to 3m times the velocity of R. And so this used to be negative, but now it's going to be 0. And so we'll actually get a smaller final resultant velocity for R, since it would used to be 4m v naught minus a negative value for m v q, as opposed to just 4m v naught divided by 3m. So I think either one of those justifications should work for part D, whether you want to use your bar chart in A or the graphical representation in part C. And I think that's everything for question 2. Yes, that's part D. Yep, that's everything.